Good afternoon, everyone, and welcome to our July 2019 webinar. And just as a quick note, as we get started here, we'll be moving our webinars to, for most months, the third Friday instead of the third Thursday going forward. So just to let you know, that's a change that's going to be happening. And it's based on some scheduling issues and so forth, but it'll work out best for everybody that has to deliver the webinars over time. And so just want to make sure you knew that. Now, this month's webinar is on the topic of algorithmic Wi-Fi. Understanding algorithms can make you a superior wireless engineer. My goal in this webinar is not to teach you every algorithm in the 802.11 standard. We're going to go over 2 or 3 of them, and I'll talk about a couple of other ways to think about algorithms as well. But it's really to get you thinking about how to think algorithmically, because when you begin to think algorithmically, you solidify your understanding of how things work. For example, you could define, though it would be complex defined as a single algorithm, you can define the algorithm or algorithms that are used for a particular wireless device to determine if it can communicate or not, based on CSMA-CA, whether it's DCF or EDCAF. The point is that you can actually determine, based on decisions made, algorithmic decisions made, when a device is allowed to communicate or that a device is not allowed to communicate at a given moment. So understanding algorithms is a key part of understanding all the processes that go on in Wi-Fi communications, in cellular communications, IoT communications, how sensors work, all the rest of the things that we deal with in wireless these days. So having an algorithmic mindset is a big key in being able to successfully understand how all of these technologies work. You can then work through those algorithms that are either directly defined for you to understand exactly how they work, or that you define as an algorithm so that you can, in your own mind, comprehend the actual process fully. Now, many people do this, but they've never stopped to think about the fact that they're actually thinking algorithmically. So while you may not have defined it as that, as we go through this, you're probably going to actually understand that you've been thinking this way in a lot of areas already. We already do it in our everyday life. When you come to a stop sign while you're driving, you use an algorithm to determine if you're the next to go or not, right? So algorithms are used in our lives. We just don't use the fancy term for it every day. We think of it as a decision, but decisions are based on algorithms. So we'll get into that as we go along. Remember, we're on Twitter at CWNP, and I'm at Carpenter Tom. Someone asked me one time why I'm not Tom Carpenter, and the reason is it was gone. So I was a little late to Twitter in around, I don't know, 2009 or 2010. And so I couldn't get Tom Carpenter, sadly. But at any rate, I'm at Carpenter Tom. So here we go. Now, first of all, the thing we want to talk about is just the general concept of an algorithm. And I've defined it as simply as I could come up with here. Algorithms are calculations that receive inputs and produce outputs. Okay, so that is effectively an algorithm. You've heard me say in the previous months that artificial intelligence equals algorithms. That's effectively what artificial intelligence is. And so that's what we're dealing with when we look at that. Network transmissions are driven by algorithms. There are algorithms that are used to determine the data rate to use for communications and wireless networking, algorithms that determine how the data should be modulated, algorithms that are used to calculate codes to actually be transmitted in place of the data stream, etc. So there are algorithms involved in network transmissions. I did a vlog the other day on smart antennas and talked about the fact that smart antennas are really antennas with algorithms behind them. So there is no such thing as an actual antenna that's smart, because antennas simply respond to the laws of physics. They do not think about what to do. Things just happen through them or on them. And so when an electromagnetic wave gets to that antenna from a wire, it simply leaks out of it. There's nothing the antenna can really do to stop it. It's just going to leak, right? And when an electromagnetic wave is passing through the air and comes by the antenna, Some of it is absorbed into that antenna or pulled along that antenna for transmission is a better way to say it. And so it just happens by the laws of physics. The antenna is not intelligently thinking about anything, and neither are the things we call smart antennas. They are simply dumb antennas that have some type of processor, some type of intelligence behind them. The purpose today is not to get into smart antennas and how they work, so I won't go further than that, but they are antennas with algorithms behind them. Modulation is really an algorithmically selected waveform, right? So you have different waveforms that represent different bits with different modulation types, and we have algorithms to pick which waveform we're actually going to generate. And you know what? Even wireless professional success, we could call that a soft algorithm. You'll see why I say that a little bit later on. So let's get started looking at some of these algorithms. Wi-Fi algorithm number 1, converting a passphrase to a pre-shared key. So what are we talking about here? Well, there's actually an algorithm defined in the standard for doing this. So if you've ever wondered what the magic is behind typing in a passphrase in an access point, for example, instead of actually typing some hex value number or something, there is no real magic. It's just that the actual pre-shared key is generated from the passphrase based on the algorithm we have here. So what we do is we perform a function. It's the PBKDF2 function. This is a hashing function that takes some inputs and generates an output. How big is the output? Well, the output's 256 bits. That's defined in the last part of this function where you see the 256/8. And what's that 4096 in the list you see? Well, that's how many times we hash it. So we hash the passphrase and SSID combined, not one time, but 4096 times. And the result is a 256-bit number or value that came from the passphrase and SSID using, again, this externally defined function. Now, you can look online and see how the PBKDF2 function works. My goal here is not to necessarily define that function for you today, but you can not only define how it works, you can find where people have put online forms where you can plug in these different parameters and it can generate the values for you. Now, in addition to giving this function, formula, or algorithm within the standard, they also define test cases. In other words, within the standard, they have, if I remember right, it's 3 different test cases where they say if your passphrase is this and your SSID is this, then your PSK algorithm should generate the following number. So in other words, you can take your algorithm you've created to implement in your access point or in your client drivers, and you can actually use the same passphrase and SSID in those 3 test cases and see if you generate the same number. Because if you generate a different number, there's something wrong in your algorithm, right? That's the point. So they give you test cases so that you can test your algorithm to make sure it's implemented right. And of course, they have to be implemented right, otherwise things won't work, right? If you have clients that have not implemented this algorithm correctly, then when they communicate with an AP that implements it correctly, they're going to be using a different PSK, aren't they? Because they've got something off in the actual 256-bit PSK. And the end result is that when they try to authenticate, they cannot authenticate. So they give you test cases. So as you're developing your drivers, your supplicant software, what have you, you can make sure that you're implementing this appropriately. So that's Wi-Fi algorithm number 1. One of the simpler algorithms. The function itself is fairly complex, but with a little bit of time, even if you don't understand advanced hashing or encryption mathematics, I think you could study some of the detailed explanations of PBKDF2 and begin to grasp that if you wanted to. The goal here is to know that there are multiple components that go into the actual algorithm. It's not just the passphrase. We also have the SSID and other values. Again, this algorithm is defined in the standard. What about Wi-Fi algorithm number 2? You may have wondered about this in the past. A wireless device sends a data frame. And then if the data frame is not delivered successfully, meaning that an acknowledgement frame or a block acknowledgement frame is not received in reply, how long does that device wait before it assumes the transmission failed. I mean, have you ever wondered about that? Kind of makes sense to think, hey, there should be something that determines that. Well, the good news is, guess what? There is something that determines that. And it's an algorithm. The algorithm that determines how long a device waits after sending a frame before it assumes it failed and then queues that frame up for a retry attempt is a SIFS time plus a slot time plus a RX5 start delay. Now, if you've studied the 802.11 standard or even just studied CWNA level material, you've heard of a SIFS, a short interframe space. You've heard of slot times. You may not have heard of this thing called RX5 start delay. That might be a new one for you, but it's key in this calculation of determining if a frame has determined or if the station determines that a frame has failed to be delivered. So first of all, the short interframe space can vary by the physical layer. The slot time can vary by the physical layer. And the RX5 start delay can vary by the physical layer. Now, some physical layers share the same value for these three, and they're obviously going to be within a band, 2.4 versus 5 gigahertz and so forth, but they do vary. So there's not just a fixed number that says, well, I wait X microseconds and then I assume it's failed. No, it depends on the PHY that I use to transmit it. Now, let me be clear. It does not depend on the chipset capabilities that I use to transmit it. I might have an 802.11n chipset, but I might have transmitted it with an 802.11g physical layer like ERP, right? I might have an 802.11ac chipset, but I might have just transmitted a frame with OFDM or 802.11a. So this is determined by the PHY I'm using to transmit, not the capabilities of my chipset. I have to abide by the rules of the PHY, the physical layer, okay? So that's why these are defined in varying ways. For example, just in case you care, the actual characteristics are defined in the 802.11 standard. And going all the way back to DSSS, the direct sequence spread spectrum physical layer. That is original 802.11, 1 or 2 megabits per second. The RX PHY start delay was 192 microseconds, okay? The slot time was 20 microseconds within that level, all right? So this kind of gives you an idea of what some of these parameters might actually be. But if we were to go to the HT physical layer, which is 802.11n, right? Now we're looking at a little different set of values. For example, we're looking at the value for an RX PHY start delay that is 28 microseconds or 24 microseconds. Well, it's 28 microseconds if you're in a mixed environment. It's 24 microseconds if you're in a greenfield environment, which hardly any of us were ever in, right? So that's going to vary a little bit there. The SIFS time, by the way, in 802.11n is 10 microseconds in 2.4 gigahertz, but it's 16 microseconds in 5 gigahertz. And the slot time, well, it varies. In a 2.4 gigahertz band, it's 20 microseconds or maybe 9 microseconds, depending on exactly what you're doing for backward compatibility. And in a 5 gigahertz band, the slot time is 9 microseconds. Okay, so you can see these different. Now, I'm not asking you to memorize all this information that I'm sharing with you. What I'm simply doing is pointing out to you that these parameters that are fed into this algorithm are dependent on the physical layer. They're defined in the 802.11 standard. And using this information, you can calculate the algorithm and understand how long it would wait and how it's going to vary for different physical layers. Now you might wonder, okay, well, why does that even matter? Well, obviously, based on this formula, a 1 or 2 megabit per second DSSS transmitted frame is going to take longer to decide that the frame has not been delivered successfully than an HT or 802.11n transmitted frame. Because remember, when we talked about the DSSS PHY characteristics, the RX PHY start delay itself is 192 microseconds compared to, remember, 24 microseconds or possibly 28 microseconds for 802.11n. So obviously, I'm going to sit there longer thinking, okay, I wonder if it's there yet. I wonder if it's there yet. I wonder if it's there yet for a 1 or 2 megabits per second than I am for a, say, 150 megabits per second, 802.11n transmission. So not only is the data rate faster with the higher rate PHYs, but the delay between a retry on a frame that needs to be retransmitted is shorter. So even if I'm in an environment where maybe some interference caused the frame to get corrupted and not be able to be received, so I never got an acknowledgement back, and then I have to retransmit it, with HT, I'm better off than I am with DSSS, generally speaking, because of this longer delay. Okay, so there's a lot of factors that improve enhanced performance other than just data rate. So we often think about data rate. And as the new PHYs come along, well, they gave us higher data rates, but they did other things too. Like we don't wait as long before we decide that that frame must have failed to be delivered and we queue it up again. So there are many factors that have been enhanced over the years to improve performance. And when you study these algorithms in the 802.11 standard, guess what? You begin to discover those things. So very useful for consideration. Now, I know some of this is a bit technical, and the important thing to keep in mind is I don't expect you to fully and completely comprehend everything today, but understand the benefits. We're starting to learn some things by studying this. We're learning that there are different variables in different PHYs. We're learning that the newer PHYs don't wait as long compared to the older PHYs before they would attempt to retry a frame. So these kinds of things can really begin to enhance your thinking about how wireless actually works. All right, let's look at Wi-Fi algorithm number 3. How does a quality of service or EDCA data frame, interframe space, or how is one calculated? So how do we calculate the interframe space? The reason this is important is because all of the other interframe spaces that are used commonly, like the short interframe space, the DCF interframe space, the reduced interframe space, though it's been deprecated in 802.11ac and so forth. These different interframe space, how they're calculated is simply they're defined by the PHY. So the PHY says how long they are, okay? And it's the end of the story. The AIFS, or the arbitration interframe space, is a little different. Now let me back off for 1 second, no pun intended, since we're talking about determining when we can communicate. So let me back off for a second and indicate that the interframe space is the amount of time we wait that must be delayed before a frame can be transmitted. There needs to be a gap, right? Before we can send, even if we're allowed to send. So you've got this whole process where you look at your timers that are set within your supplicant or your client device. You look at your random back-off timer. You look at your duration field value called the network allocation vector. You've got to wait till all these things count down. When they all count down, you still have to wait an interframe space, even when you determine that the medium is idle and you're allowed to talk. The reason for that is that important frames like acknowledgement frames, they get a short interframe space before them. And notice that part of the actual algorithm that determines how long an arbitration interframe space is we add an ASIFS time. We add a short interframe space. So we calculate part of it, then we add a short interframe space. So even the arbitration interframe space, which is used to give higher priority to some traffic than other, is always going to be longer than a short interframe space. What that does is it makes sure that a station that's waiting to send an acknowledgement frame is more likely to get access to the medium and send that back. Before what? Before this algorithm, number 2 that we looked at, ends up determining it needs to retry, right? So if the ACK is delayed, then a station goes into retry mode when it doesn't necessarily need to do so. So short interframe space is used for those types of frames. So the arbitration interframe space, the first thing you'll notice is some special notation in this algorithm or this formula or function. You'll notice that in brackets, it has AC. So the arbitration interframe space varies by AC. Now, what is AC? Well, I'm in Ohio and we're under heat warnings right now. It's only in the 90s for those of you that live in Phoenix and Las Vegas and even hotter parts of the world. It's only in the 90s and we're under heat warnings. But anyway, the AC is not the air conditioning in this case. It's the access category. And so AIFS differs per access category. Now, the way it works is you have something called an AIFS number defined for each access category, and you multiply that times the slot time, which, remember, is also defined varying somewhat by the different phis in the different bands. And so therefore, whatever this AIFSN is set to, which can be configured in some systems, we multiply that times the slot time. And then remember, order of calculation is left to right, but always do multiplication and division before addition, right? That's the standard order of processing in these types of formulas. So therefore, we know we're going to multiply the AIFSN for the access category by the slot time, and then simply add to that the CIFS time. And we're going to come up with some number in microseconds that we're going to wait. Okay, so that's how we determine that arbitration interframe space duration. And this, by the way, exact text taken right out of the 802.11 2016 standard. And so was this, and so was this. Okay, so these are direct text for the algorithm or formula that is the algorithm that's pulled out of the 802.11 standard. Now, why is it important then to begin to study these algorithms? I'm going to suggest to you maybe a bit of a novel idea. It's not just about understanding the specific algorithm, but it's about putting all the pieces of the puzzle together that make 802.11 work. When you begin to study these different formulas or algorithms, and you begin to look at each of the component pieces, and you figure out what is a slot time and why in the world do I care, and what is the short interframe space time and why do I care, and etc., then as you figure those pieces out, and then you put the pieces together in different ways they're used, everything that maybe you just kind of memorized to pass an exam begins to make a lot of sense. Things start to click, and you really begin to have what I like to call those light bulb moments, those moments when you have an understanding for exactly what is going on with wireless communications. Okay, well, let's look at algorithm number 4. This is not from the standard. We're going to answer a different question. How many APs are required? When you see this nice little long italicized F in a formula, it means function. And when you see that something equals this function, it often means that it's a function of, okay? So the total APs is a function of a few different parameters. Now, this is not intended to be exhaustive. This is intended to help you think how you might create some of your own algorithmic ways of thinking. So in other words, you can think of answering the question, how many APs are required, as a function of the required capacity, the coverage area, the attenuation factors, the total number of clients per client type, and then the total number of clients beyond that, and possibly even other parameters. So I'm not telling you this has everything in it that ought to be in the function, but I'm telling you it's a way to think somewhat mathematically about how to answer questions like this. And when you begin to do this, it forces you to think about, well, what are all of the things that I have to consider when I'm determining the total number of APs? In fact, if you can think of anything right now other than required capacity, coverage area, attenuation factors, the total clients per type, go ahead and put it in the question and answer period. What are some other things we might have to plug into our function here to be able to answer how many APs are required? Go ahead and put that in, and we'll review some of those when I'm finished with the rest of this presentation here in 5 minutes or so. So what I'm saying is, when you think of my question is a function of all of these things, it's a great way to wrap your mind around the things that have to be considered in something. And a lot of people who try to think mathematically will do this a lot. They'll say something is a function of. Now notice, I don't have a specific number for required capacity, right? And required capacity, guess what? I may need another algorithm. Required capacity is a function of something else, right? Coverage area, attenuation factors is a function of the materials and their reflectivity index and their attenuation rating, and on and on. So the point is that there are many, many different ways that I can use this as a thinking tool. I've found this to be invaluable as a thinking tool. So I'm making all the things I need to consider plug into some type of an algorithm, and it helps me to conceptualize it, think about it, and also remember it better, okay? Because part of this process is in some ways I'm simplifying it. Because think about it, each one of these could be their own algorithm, couldn't they? And some algorithms are soft algorithms. In other words, there might be one way to calculate required capacity in one scenario and another way to calculate it in another, and so on. So we might call those soft algorithms because there's not necessarily a hard answer to all of the elements of the function. And that brings me to my final algorithm, algorithm number 5, which I call a soft algorithm. How do I get ahead as a wireless engineer or professional? Now you might think, well, this is Tom Carpenter, CTO at CWNP. He's going to tell me it's a function of my certifications. Well, let me put it this way. Success as a wireless engineer professional is a function of technical knowledge, relational abilities, and self-management. And technical knowledge is a function of however you're getting that technical knowledge, right? Maybe you are getting a lot of it through certifications, but you're going to get a lot of it through experience too. You're going to get a lot of it through research, right? And even if you get, let's say, CCIE wireless with Cisco, guess what? There's still going to be a multitude of times when you're dealing with a problem and you've got to go dig and do research because you didn't learn anything at all during the process that helps you solve the problem you're trying to solve. And I'm not trying to say something negative about the CCIE wireless certification, because guess what? They're going to be people who become a CWNE, go through all of our training and certifications and have 3 years of experience. And then they're going to go and they're going to encounter a problem and they're going to say, I've got to go do some research, because even experts don't know all the answers. Okay. Even experts don't know all the answers. In fact, I've often said and heard others say it too, that what really defines that you've reached expertise is your awareness of how much you don't know. A true expert in any field can say, I've gotten to the level where I know more than most people, but I also know I don't know most of what there is to know. And that's that level where you finally reached expertise, right? So what do I mean when I say that success as a wireless engineer is a function of your technical knowledge, your relational abilities, and your self-management? Well, the reason I like to share this is years ago, I came up with a concept that I call the foundations of effectiveness. 3 foundation stones to help you be successful as a technical professional. And it doesn't matter if you want to be an AWS solutions architect, engineer, if you want to be a programmer with Visual Studio, if you want to be a web developer, a wireless engineer, it really doesn't matter. The same foundation stones are there. What changes is the size of the stones, how important they are. And that also changes depending on what you're doing in your area of expertise. So when you're the engineer who does the implementation, administration, planning, design, troubleshooting of a system, your technical knowledge becomes extremely important. When you're managing the engineers that do all of that, your relational abilities become more important. Okay, so it depends on what you're doing in the role within the industry. So technical knowledge is a given. You're not going to be able to get ahead if you don't know your stuff. So that's a given. The problem with many of us in the information technology and information systems worlds is that many of us think that that's the key to success, but it's actually just one of the keys. And depending on where you are in your journey, it can become a more or less significant key. Relational abilities are actually one of the most important. The ability to listen. I mean, think about it. If you're getting ready to design a wireless LAN and you lack listening skills, you're going to implement the wrong thing, because when you're doing requirements analysis, you're not listening, you're not gathering information and getting the right inputs so you can give the right design, right? So listening becomes very important. Communication. Imagine you're troubleshooting something and you've got to go now communicate the reason why they need 70 more access points, or the reason why they need to turn off the radios in 70 of their access points in 2.4 gigahertz. Whatever it is, you've got to explain to some manager, hey, you've bought all those access points, dual band, and I'm telling you in 30% of your access points to turn off your 2.4 gigahertz radio. Well, there's something that needs some explaining. I spent all that money on it, and now you're telling me not to use what they think of as half the capabilities, right? So you need communication skills to be able to communicate the why behind the what, the benefit of it, and how that it can prove beneficial. Okay. And then there's self-management. This is about time management. It's about prioritization. It's about project management. It's about self-discipline, habits. It's about getting the right thing done at the right time in the right way. Okay. So self-management, wildly important for all of us. Now, here's where I'm going to shock you. It's my suggestion that there's no one that works in the tech industry where more than 50% of this success algorithm is technical knowledge. Regardless of where you are in the ladder, if you want to call it a ladder, regardless of what your role is, whether you're currently in the trenches doing the tech or you're a project manager or you're a department head, no one in the industry, in Tom Carpenter's humble opinion, requires more than 50% of this algorithm be technical knowledge. It's relational abilities and self-management. And depending on your role, it may be as little as 15 or 20% of your required knowledge. So keep that in mind. Now, you might be like me. I'm a geek. I love tech. And whether I still needed to learn the deep ins and outs or not, whether I still needed to study these first three algorithms we looked at right out of the 802.11 standard or not, guess what? I'd still be doing it just because I like it. But I want to make sure I'm investing in those other areas that are key to my success as well. So I thought I'd leave you with a nice algorithm to think about your career and some things you might want to consider there. Well, at this point, we've ended our journey of algorithmic thinking, and we've looked at some Wi-Fi algorithms that are right out of the standard. We've looked at how we can think about other things in our decisions related to wireless networking and communications by creating what we might call conceptual or softer algorithms. And we even looked at a soft algorithm for success based on what I've developed years ago called the foundations of effectiveness: technical abilities, relational abilities, and self-management abilities. With that, we've delivered what we've scheduled to deliver, and I'd like to thank you for attending.